So, let's go. Right now, 25.8 billion kilometers away. A machine with less computing power than a pocket calculator is being shot at by exploding stars. The only thing standing between it and oblivion is kitchen foil. Literal kitchen foil. And it's running out of power, running out of time, and heading into a darkness so total that the sun is just another dot. These are the 6 most terrifying things Voyager 1 will encounter before it dies. Number 6, the bullet storm. You need to understand where Voyager 1 is right now, not where it's going. Where it is, because it's already in trouble. On August 25th, 2012, Voyager 1 crossed the heliopause. That's the boundary where the sun's solar wind, this massive stream of charged particles blasting outward in every direction, finally loses the fight against the pressure of interstellar space. Inside that bubble, you're shielded. The sun is actively pushing back against the galaxy's background radiation. Cosmic rays, high-energy particles launched by supernovae halfway across the Milky Way, most of them get deflected before they ever reach you. Outside that bubble, there is nothing between you and them. Voyager 1 is outside. After crossing, it measured cosmic ray intensity 15 times higher than what you'd get near Earth. These aren't gentle particles. A single cosmic ray proton can carry the kinetic energy of a baseball thrown at full speed, compressed into something smaller than an atom. They move at nearly the speed of light, they punch through metal, they punch through circuitry, they flip bits in computer memory, and there is no dodging them. A cosmic ray physicist at Caltech who's been on the Voyager mission since the launch put it simply, "We are dodging bullets out there." In 2023, one of those bullets probably hit something important. A cosmic ray appears to have destroyed a memory chip in Voyager 1's flight data subsystem. The spacecraft went dark for 5 months, not dead, but incoherent. Gibberish. Engineers at JPL had to remotely rearrange code around the damaged section of memory, debugging a computer built in the 1970s across a gap of 24 billion kilometers with a round-trip communication delay of nearly 2 days. They pulled it off. But it's the kind of fix you only get so many times. And the radiation shielding? Before launch, engineers wrapped some of the cables in aluminum foil, not aerospace-grade foil, kitchen foil. The kind you wrap leftovers in, that was to protect against Jupiter's radiation belts, which the spacecraft passed through decades ago. Nobody planned for interstellar space. That foil is now the last line of defense between Voyager 1's aging electronics and the full, unfiltered fury of galactic cosmic rays. Every single day it survives is borrowed time, but the bullets aren't even the scariest part. Because at least the bullets are fast. Number 5, the slow suffocation. The cosmic rays are random, you can't predict them, can't prevent them, can't do anything except hope they miss. But there's a different kind of death happening to Voyager 1 right now that's completely predictable, totally unavoidable, and already well underway. Voyager is starving. Whereas 3 small devices called radioisotope thermoelectric generators power the spacecraft, they run on the heat of decaying plutonium-238. When Voyager launched in 1977, those generators produced about 470 watts. That's less than a microwave oven. But it was enough to run 10 scientific instruments, a radio transmitter, heaters, and 3 onboard computers. The problem is that plutonium decays. Every year, Voyager loses about 4 watts of electrical power. On a spacecraft where every watt is a life or death decision, 4 watts is the difference between keeping an instrument alive and killing it forever. So engineers have been choosing which senses to murder. One by one, over decades, cameras, spectrometers, heaters, gone. In February 2025, they shut down the cosmic ray subsystem. A month later, they killed an instrument on Voyager 2. By 2026, Voyager 1 will be down to 2 instruments, a magnetometer and a plasma wave detector. That's it. 2 senses left on a machine that launched with 10. The Voyager project manager at JPL said it plainly. If they hadn't started shutting things off when they did, the mission would have ended within months. The cameras are a particularly cruel detail. They were turned off in 1990, right after Voyager took the pale blue dot photograph. After that, the camera software was deleted from the spacecraft. The ground computers that could interpret the images were decommissioned. Even if you could somehow turn the cameras back on, the software doesn't exist anymore. And it's too dark out there to see anything anyway. Voyager 1's eyes were not just closed, they were removed. And there's exactly one antenna on Earth that can send commands to either Voyager. One. A 70-meter dish in Canberra, Australia. When that dish went down for maintenance in 2025, nobody could talk to either spacecraft at all. For months. Right now, Voyager 1 transmits with a radio power of about 22 watts, roughly the brightness of a refrigerator light bulb. By the time that signal crosses the distance to Earth, it carries less energy than a falling snowflake. NASA's dishes can still hear it. For now. But the starvation isn't even the scariest part. Because what's coming next is a kind of loneliness no human has ever had to think about. Number 4. One light day. This one hasn't happened yet. It's coming in months. November 2026. Or roughly November 13th. That's when Voyager 1 is projected to reach a distance of one light day from Earth, 25.9 billion kilometers. The first human-made object to ever be that far away. Here's what one light day actually means. You send a command right now, it doesn't arrive until tomorrow. Voyager replies immediately, you don't hear back until the day after that. A single yes or no question takes 48 hours. When Apollo astronauts talked to mission control from the moon, the delay was 2.6 seconds. From Mars, it's up to 4 minutes. From Jupiter, up to 52 minutes. From Pluto, up to 6.8 hours. From Voyager 1, 24 hours. We used to measure spacecraft distances in millions of kilometers, then in astronomical units. Now we measure the distance to our own machine in days of light. That's not engineering scale anymore. That's astronomical scale. Voyager has crossed the line between something we built and something we released. If you could drive to it at a highway speed, 100 kilometers an hour, nonstop, it would take you about 29,500 years to arrive. And here's the thing about that distance, everything we've talked about so far, the cosmic rays, the power death, the thinning signal, that's the before it dies part of this video. What comes next is the after. And the after is where the countdown gets truly terrifying. Because the most frightening thing about Voyager 1 isn't what will kill it, it's what happens when nothing does. Number 3, the 30,000-year graveyard. Sometime around the year 2300, give or take, Voyager 1 will reach the inner edge of the Oort cloud. If you haven't heard of it, here's the short version. The Oort cloud is a theoretical shell of trillions of icy objects surrounding the entire solar system, way beyond the planets, way beyond Pluto, way beyond anything we've ever seen directly. It was theorized in 1950 by an astronomer named Jan Oort. We've never observed it. We think it's there because of the orbits of long-period comets. The inner edge begins at maybe 2,000 astronomical units from the sun. The outer edge might extend to 100,000 or even 200,000. Voyager 1 will take about 300 years to reach the inner edge. It will take roughly 30,000 years to pass through entirely. 30,000 years. 30,000 years ago, humans hadn't invented agriculture. We were painting animals on cave walls. We hadn't built a single city, written a single word, planted a single crop. The entire span of recorded human civilization, every empire, every war, every book, every song, all of it fits inside the time it will take Voyager 1 to cross this one region of space. And this region is still technically part of our own solar system. During all of that time, Voyager will be completely dead. No power, no signal, no instruments, just a 733 kilogram piece of metal, silicon, and gold tumbling silently through a cloud of frozen debris that no human eye has ever seen. Now, despite the name cloud, the Oort cloud is almost entirely empty space. One astronomer calculated the odds this way. Imagine you took 96 million styrofoam balls and spread them across the entire surface of the Earth. The odds of finding one in your backyard are still 100,000 times better than Voyager hitting an Oort cloud object, so it will almost certainly drift through without touching anything at all. 30,000 years of silence, of nothing, of a dead machine coasting through a graveyard it can't see. Now, I have to be honest with you here. The Oort cloud itself has never been directly observed. It's mainstream science, well supported by comet data, but still theoretical. And beyond that, some scientists think rogue planets, free-floating worlds untethered to any star, might be lurking out there. One researcher put it this way: a mildly close encounter with one of those could completely change Voyager's trajectory. But that's speculation. Nobody knows what's actually out there, which might be the most terrifying part of all. But not the most terrifying thing on this list, because we haven't talked about what happens when Voyager finally reaches another star. Number 2, the near miss. After the Oort cloud, after tens of thousands of years of drifting dead through nothing, Voyager 1 will finally approach another star. In roughly 40,000 years, it will pass within 1.6 light years of a small red dwarf called Gliese 445 in the constellation Camelopardalis. Right now, that star is about 17 light years from Earth, but it's moving toward us. By the time Voyager gets there, Gliese 445 will be one of the closest stars to our solar system. 1.6 light years sounds close. It is not close. Why, if the entire solar system were the size of a quarter, a small coin you could hold between your fingers, Gliese 445 at closest approach would be about 6 kilometers away. Light itself takes nearly 2 years to cross that gap. Voyager will not enter the star's system. It will not be captured, it will not orbit, it will not slow down. It will drift past completely unnoticed, a dead speck of metal in a void so large the star won't even gravitationally acknowledge it exists. That's the closest Voyager 1 gets to another star for 40,000 years. And it's not close at all. Further out, the numbers only get more absurd. In about 303,000 years, Voyager passes within roughly 1 light year of a main sequence star. That's actually its closest predicted stellar approach ever. 1 light year. Still not close. In 570,000 years, it brushes past 2 more stars. In 5.7 million years, it exits the local bubble, the low-density cavity of space carved out by ancient supernovae that our entire solar neighborhood sits inside. And after that, it just keeps going. No star captures it, no planet stops it, no collision ends the journey. It just drifts and drifts and drifts into a silence that makes everything before this feel small. Which brings us to the number 1 most terrifying thing Voyager 1 will ever face. Number 1. The billion-year drift. The most terrifying thing about Voyager 1 is that nothing will destroy it. It will orbit the center of the Milky Way. It will complete a full lap roughly every 225 million years. And it will keep doing that, lap after lap, for a length of time that breaks the human brain. The estimated timescale before Voyager 1 collides with a star is 10 to the 20th power years, a 1 followed by 20 zeros, 100 quintillion years. The universe right now is about 13.8 billion years old. Voyager's expected lifetime before it hits anything is roughly 7 billion times the current age of the universe. If the entire history of the cosmos, from the Big Bang to this exact moment, were compressed into a single second, Voyager would drift for about 230 years before something finally stopped it. In 4 to 5 billion years, the Milky Way will collide with the Andromeda Galaxy. The Sun will swell into a red giant. It may consume Earth. Our planet might not exist anymore, but Voyager will. Still drifting, still intact, still carrying what it carries. Interstellar dust will erode the spacecraft over millions of years. Slowly, atom by atom, the structure will pit, wear, degrade. But bolted to the side of Voyager 1 is a 12-inch gold-plated copper disc tucked against the spacecraft body with its engraved side facing inward. Protected. Scientists who modeled its trajectory and the environments it will pass through estimate that the golden record will remain at least partially legible for over 5 billion years. 5 billion years. And on that record right now, hurtling through interstellar space at 61,000 kilometers per hour, is this: 116 images of Earth. Greetings in 55 languages. The sound of thunder, wind, birdsong, whale calls, a mother's first words to her newborn, laughter, 90 minutes of music, Bach, Beethoven, Chuck Berry, and the heartbeat of a woman named Anne Druyan. During the creation of the Golden Record, Druyan and Carl Sagan fell in love. 2 days after they first told each other, she went to a hospital in New York where her brainwaves and heartbeat were recorded and compressed onto the disc. She later said she spent the whole time thinking about the wonder of falling in love, the vastness of the universe, the sheer improbability of being alive at all. Her heartbeat is on that record right now, 25.8 billion kilometers from where it was first felt. heading deeper into a darkness that will last longer than the sun. No one will hear it. The spaces between stars are too vast. The spacecraft is too small. Carl Sagan knew that. He said the act of launching it, throwing a bottle into the cosmic ocean, said something hopeful about the species that did it. The universe will not care about Voyager 1. The void will not mourn it. The stars it passes will not notice. But we built it. We aimed it at the edge of everything we knew. And we strapped to its side a golden record that says, in every way we could think of, we were here. We were alive. And we wanted someone to know.